Hello, this video is an introduction into how to write electron configuration. If you're watching this video, it probably means that you are an IGCSE student or an A-level student who has a passion for chemistry and is searching for more than the curriculum teaches you. So for example, you will come across an element, for example, like magnesium, and you'll be told the electron configuration of magnesium is 282. 282. However, if you go online and you search for magnesium electron configuration, you might come across something more like this. So this video is about what this actually means. So what these numbers actually mean is they're talking about the orbitals in the shells of the atom in question, not orbits. Orbits are the path, the circular path of, for example, a planet round a star or a point in space caused by gravity. Orbits are a little bit different. The Heisenberg uncertainty principle dictates that it is impossible to state at the same time both the position and velocity of electrons. Therefore, electrons are not in an orbit, because in an orbit we can calculate both the velocity and position of planets. So instead, what we do is that we calculate the positions of electrons at regular intervals, and by plotting them on a diagram, we can get an idea of when electron is most probably at, and the shape of the area of the electron is most probably at a particular point in time. Therefore, if we continue to plot it out, it might look something like this. So what this is an s orbital. So there are three types. These are most basic low energy types of orbital. There is the 1s, 2s, and 3s, and this will correlate to what you'll see in hydrogen, lithium, and sodium. So let us take helium for our first example. 1s2. What do these things mean? 1 refers to the shell or the level of the orbital. S refers to the type of orbital. There are S, D, P, and F orbitals, which we will be talking about. This 2 here is pronounced as 2, not as square. And this refers to the number of electrons in the orbital. So you will note that there's a maximum of 2 electrons in every orbital you come across. There can never be more, but there can be just 1. So for example, hydrogen is 1s1 because it has only 1 proton and therefore 1 electron, and helium is 1s2 because it has 2 protons and therefore 2 electrons. However, once you leave the first level and go to the second level, you'll find that there are 1, 2, 3, 4, 5, 6, 7, 8 electrons. So how can this be? If there's only 2 electrons in each orbital, there must be more orbitals for the electrons to fill. And this is so, and we come across the p orbitals. Now the p orbitals look like a sort of hourglass figure or a number 8, and there is only one type. However, they can exist in 3 different directions, as represented by y, z, and x. Now of course these y, z, and x are no fixed point in space. They will change as the atom moves around in space. However, this gives us an idea of where the electrons are. So if we come, for example, to boron, we come as it is 1s2, 2s2, 2px1. So the x represents which direction it is. Now if you come across to carbon and nitrogen, you don't find that it just goes into the p orbital, the x orbital, followed by the y orbital, followed by the z orbital. It goes into each individual one before overlapping. And this is because when 2 electrons are in the same orbital, they cause a slight, very very slight negative repel. They repel each other very slightly. Therefore, it is more stable. It requires less energy for them to each fill individual orbitals. So only after each one is full of 1 electron, then they do start to overlap, as in oxygen, fluorine, and neon. Now let us come to the third period. Okay, first of all, two shortcuts. It would be too long for us to write out, for example, sodium as the whole thing, 1s2, 2s2, 2p, 2px2, 2py2, 2pz2, 3s1. So instead, first of all, we can compress all these three into one. So 1s2, 2s2, 2p6, and 3s1. Second of all, well, this 1s2, 2s2, 2p6 is the structure of neon. Therefore, if we put neon followed by whatever is extra, it is a very efficient way of making it smaller. However, note you will not do this with helium because putting 1s2 is quicker than doing that with helium. So with this knowledge, we carry on. Sodium is the structure of neon, followed by 3s1, magnesium 3s2, aluminum 3s2, 3px, silicon 3px, 3py, and so on and so forth. Note that the same rule applies. Each electron goes into each individual x, y, z orbital before overlapping. So now you know what 1s2, 2s2, 2p6, 3s2, for example, for magnesium means. It is talking about the orbitals and which level it is. So just remember that the big number refers to the level, the letter refers to the type of orbital, S, P, D, or F. There might be an X, Y, or Z, which refers to different directions, and the letter and the small number refers to the number of electrons in that orbital. So now you know the electron configurations of all the elements from helium to argon. Well, at least in the pure atomic state, without bonding to anything. The further periods will be discussed in another project video, because when you come across into the 3D orbitals, it gets a little bit more complicated. But for now, thanks for watching, and bye.